Hi everybody, welcome to the third talk in our Astronomy and Astrophysics faculty search. What? Series.
Endless series.
It's not endless. So it's my pleasure today to introduce Dr. Allison Kirkpatrick. Dr. Kirkpatrick got her bachelor's degree in math from the University of Florida in 2007, and then went on for a PhD in astronomy at the University of Massachusetts Amherst, which she finished in 2016. She then moved to Yale University, where she's a Yale Center for Astronomy and Astrophysics postdoctoral fellow, and that's where she is right now. Well, not now, but you know what I mean. And Allison's work is really specialized on studying obscure properties in galaxies. So how active galactic nuclei, so black holes, are obscured by dust, how galaxies are obscured, and what we can interpret from those using lots of diagnostics outside the visible spectrum. So she's going to talk about that today. I'm looking forward to hearing it, so let's welcome her.
All right, so thanks everyone. Thanks for having me here. So unfortunately, in my line of work, I don't get to show you a lot of pretty Hubble pictures. So this picture up here is going to be one of the only pictures you see from me. But I like to put this picture here to give you a sense of perspective. This is the Hubble image of the good south. So each one of those dots is a galaxy. And it's a galaxy about 10 billion years in the past. And in fact, each one of those dots is probably not one galaxy. It is probably many galaxies together, blended together, because Hubble had very poor resolution. And so it is my job to look at this image and get science out of it, and to tell you something about this population of galaxies. And so I'm going to try to convince you that we know something, and to tell you what it is that we know. So since we have a room full of physicists, it's good to tell you when I study. So I like to start with the model of the universe. Of course, as we understand it, we had inflation. A few 100 million years after inflation, the first stars started to form, and then around the first stars, the first galaxies started to form. Around this time, also, the first black holes started to form. And not long after that, and we're not entirely sure when, but not long after, the first dust started to form. And in the early universe, you could see stars in the UV and the optical light, but as this dust built up, it began to obscure all of the stars and all of the black hole growth. And the peak of star formation and black hole growth occurs there. It's about 3 to 6 billion years after the Big Bang. And then gradually, things became less obscured until we get to today, with our Milky Way and other galaxies are the dominant sites of star formation, and star formation has become less obscured. And so we can look at it again in the UV and the optical. So to convince you of this, of how to put this in a more technical perspective, we like to talk about the star formation rate density of the universe. So this plot here is basically all you need to know about the universe. It's all right there. It tells you when the universe was building up the most stars, and that is at a peak redshift of 0.2. You can see this distribution peaks. So this is a co-moving box, and how many stars are being formed within a co-moving box. Star formation declines, of course, towards the Big Bang, and then it declines today. So I call this peak cosmic noon, because that is when the universe is the most exciting. Today we're in maybe cosmic tea time, moving towards cosmic old age. And not only is this the most exciting area for star formation, but we also know that the most black holes are being built up as well. These are 3 different measures of the accretion rate onto supermassive black holes at the centers of galaxies. We have to scale it by a factor of 100, but the shape perfectly matches the star formation shape. So to understand galaxy evolution, we need to be looking in the past, 10 billion years ago, and we need to be looking in the dust, and we need to be looking at black holes and stars simultaneously, because it's all being built up in this era. So to tell you what you see from the UV light is the best light for studying star formation typically, because you're looking directly at the photons from young stars. So this tells you, as a function of mass for galaxies, how much the star formation you would measure with the UV optical light in this cosmic noon era. Now, when we turn to the IR, we are measuring an order of magnitude more star formation. That's because there's so much dust in these galaxies, it's just absorbing all the UV and the optical light. So infrared light is really key. All right, So I want to paint a very broad picture of galaxy evolution for you. So we typically quantify galaxy evolution with the main sequence diagram. It's something I'm going to return to a couple of times in this talk. Yeah, okay. It's all right. It's all right. So the main sequence is the specific star formation rate of a galaxy. The specific star formation rate is the star formation rate divided by the stellar mass. You can think of the stellar mass as the integrated star formation history of a galaxy. So what you want to know is how many stars is the galaxy forming right now, that's its star formation rate, versus how many stars it formed in the past. This tells you something about galaxy evolution. So galaxies, normal galaxies like our Milky Way, live on the main sequence. They're undergoing long-lived secular star formation that will last for 1 billion years. Occasionally, some process happens, oftentimes it's a merger, that funnels gas towards the center of a galaxy and it compresses it and it fuels this burst of star formation. Okay, and so then you live in the starburst regime and your star formation increases by a factor of 10, maybe a factor of 100. It's a very short-lived, it only lasts for tens of millions of years. We think immediately following the starburst regime, what happens is that galaxies begin to quench. Their gas gets eaten up by this fast starburst phase, and they move into the transition regime where their star formation rate is lower compared to their stellar mass, and then you get a very massive red and dead elliptical galaxy. So these are very large galaxies, and they're not forming new stars. All right, so that's the general picture of galaxy evolution. I'm going to look at galaxies on the main sequence and right above it, because this is where dusty galaxies tend to live. And I'm going to, later in the talk about where black holes live in relation to this diagram. But first, I want to tell you a little bit about what you can see from the infrared. The infrared, you have just dust piled on your galaxy. It is hiding stars, and it's hiding a black hole. If you didn't have any dust, your black hole, the accretion disk around a black hole would look like this blue line. If you didn't have any dust, light from your stars would look like this red line, okay? And so that's what we would see. When you have dust, you get this, okay? So now your black hole and your stars are hidden by a cloud, and you have to radiative transfer all of that emission out. And so I see this black line, well, not even that, I see a few points on the black line, and I have to decompose it and try to figure out how much of this signature is due to black holes and how much is due to stars, okay? So for the first part of this talk, we're not going to worry about the black holes. I'm going to tell you that I've already removed them. We're just going to talk about the stars. This is an actual galaxy. This is one of my best galaxies. That's why it's in my talk. I would not show you a terrible galaxy. This is at a redshift of 0.64, or a look-back time of 6 billion years. So I'm going to tell you, here's what we can learn from the infrared spectral energy distribution. So this is all infrared light, all right? And then this is the luminosity at each infrared wavelength of light. The first thing that we want to know is something called the infrared luminosity. So this is where you fit a model and you integrate, typically for no good reason at all, from 8 to 1,000 microns. There's no physical reason behind that, okay? But this presumably is all dust heated by young stars. So you should be able to look at your UV and your optical and see very, very low star formation rate, and that's because all of that light is coming out right here. So we measure the infrared luminosity, and then we just directly convert it to a star formation rate. Now that has some problems. One of them is hidden black holes. The other is old stars, because old stars can also cause some of this heating. Okay, the next thing that we can do is determine the temperature of all of the dust in the galaxy. And we do this by fitting a modified blackbody spectrum, and where it peaks is the dust temperature. You'll notice that the dust temperature doesn't fit these points out here. That's because we can modify this to get the dust emissivity. We can fit that slope to get the dust emissivity. The dust emissivity tells you something about the metallicity, the dust grain properties, the shape of the grains, how well they absorb light, how well they remit it. In this case, I'll actually tell you a fun thing about this galaxy. This is probably 2 galaxies blended together. And I know that because the emissivity is so bad. It's like an emissivity of 1, which is really shallow. And so that's one of the ways that we know that some of our data in the submillimeter is blended with other galaxies. All right. If you have a spectrum, you can get certain emission lines that will tell you the kinetic temperature of the gas and the electron density of the gas. It will tell you some properties of the ISM. And then finally, you can take this lone data point out here and convert it to a dust mass of your galaxy. The entire dust mass of your galaxy you just get from one data point. It has to do with the fact that longer grains emit at longer wavelengths, or larger grains emit at longer wavelengths. Okay, so what we used to think is that infrared luminosity is all you needed to know about a galaxy. So before Herschel came along, there was the IRAS Space Telescope, and the IRAS Space Telescope was used to classify galaxy shape just according to infrared luminosity. So each one of these templates is a step up in luminosity, and you can see how the shape is changing. The peak is shifting. These features in the middle, which are called pH features, are getting lower with infrared luminosity. And in fact, there's a well-known relationship between infrared luminosity and dust temperature. Right? So infrared luminosity is down here, dust temperature is here, strongly correlated. So all you need to know about a galaxy is its infrared luminosity. And then you can infer everything else about it. You can infer its dust temperature. You can also infer something about its structure as well. And this idea was just taken and blindly applied to high redshift galaxies. We just assumed that galaxies 10 billion years ago behaved in the exact same manner. But with Herschel, we now know that that is not true. So we now know that galaxies 10 billion years ago are colder. You can see the peak shifting there. That has to do with dust temperature. So this goes from redshift 0 out to redshift of 2. We also know that they have more cold dust. You can see how the Rayleigh-Jeans tail has shifted. That's due to an increased presence of cold dust in your galaxy. And of course, it's parameterized down here in the bottom. You can see the local relationship between infrared luminosity and temperature and the high redshift relationship. So the big question was why? The initial answer was that these galaxies have a central starburst. Okay, so all their star formation is in the center. It's very hot, but they just have a lot more dust dumped on them. So they're just more extended. And if that's the case, then this radiation from the center just takes longer to get out, and it gets depleted as it's moving throughout the galaxy. So you'll naturally see a colder dust temperature. All right, there's problems with that. We know what high redshift galaxies look like. This is what they look like. They don't look like a central starburst with like a dark dust disk. They look like, to the degree that we can see them, they look like normal star-forming galaxies. You see knots of star formation here, here, and here, and they look like a disk. We've also measured it using the gas. So these are the sizes of infrared luminous galaxies from 0 out to redshift of 2. These are a local population called ULIRGs. Okay, so local, very dusty galaxies are small, but their high redshift counterparts are not small. They're big. Okay, and we also know, we've now measured with ALMA, that the star formation radius traces the radius encircling half the stellar mass. So that's what I was telling you. There's clumps of star formation all throughout the disk. So these are not a central starburst with more dust just dumped on top. So what is going on? So to get at this question, I did a case study of very well understood samples. So I had a sample, again, of, these are Spitzer images, from the Goods fields. I selected galaxies based on their mid-infrared spectra. So I selected purely star-forming galaxies at redshifts of 1 to 2, so 7 to 10 billion years ago. And then I took local samples with the exact same infrared luminosity, so presumably the same amount of dust, because we think infrared luminosity correlates with dust. And I also selected purely star-forming galaxies. And I calculated all of the dust masses self-consistently. So what I found is that dust masses, there's a strong correlation between infrared luminosity and dust mass. So that's seen up here. That holds for all samples. The purple and the green samples are the local samples. The orange is the higher redshift 7 to 10 billion years ago sample. Okay, strong correlation between infrared luminosity and dust mass. That was expected. But if you focus in on these particular galaxies, the higher redshift galaxies have more dust. They have about 5 times more dust. And it's easier to see down here where you just take the ratio of these two parameters. There is one relationship for local galaxies and one for higher redshift galaxies. Okay, one for higher redshift galaxies has moved over more. Now, unless you are a far-infrared astronomer, it doesn't make a lot of sense to think about infrared luminosity versus dust mass. So this is a much simpler parameter called the star formation efficiency. It is how efficiently you are converting your interstellar material into new stars, okay? Because this LIR correlates directly to a star formation rate. So what this tells us, if we think about this as a star formation efficiency, is at a given infrared luminosity, higher redshift galaxies are less efficient at forming stars, okay? So this is kind of counter to our previous mode of thought. We kind of thought that higher redshift galaxies would be more efficient at forming stars, but they're not. They're less efficient. There is, however, a universal relationship between infrared luminosity over dust mass and dust temperature. So all of the galaxies kind of are very correlated. They lie along the same relationship, which is shown in black. The reason for this is because this drives your interstellar radiation field. So your infrared luminosity is the amount of light coming out of your young stars. The dust mass is the amount of material it has to move through. So if there's more dust, your interstellar radiation field is depleted. Your dust temperature is sensitive to the amount of light hitting it, so the interstellar radiation field. So of course these things are correlated. What's interesting about this is that the theoretically expected relationship is the dotted line. So the measured relationship doesn't match up to it, and there's a lot of scatter. We don't really know why. These are open questions. These are things that will take ALMA observations to really resolve the interstellar medium in these galaxies.
Can I ask you a question?
Yeah.
The theoretical relationship, what is that theoretical relationship based on?
Yeah, okay. So the theoretical relationship is just a modified black body. If everything was fit by one temperature in a galaxy, if it was all homogeneous.
In any individual galaxy?
In any individual galaxy, it was homogeneous, you should see a slope of 4 plus beta. So it's not homogeneous, of course. So that's one problem, is how to model the different dust temperatures and what you would expect. So one of the things I'm not going to talk about in this talk, but I showed in local galaxies, is that you theoretically do expect a relationship of 3 plus beta, and I measure that. So I've done this same work on a resolved scale in local galaxies. So this is that same LIR over M dust parameter, and then this is dust temperature, and they trace each other very nicely. So the takeaway is that dust temperature is not proportional to LIR in and of itself. That's an incomplete idea. Temperature is proportional to LIR divided by dust mass itself. Okay.
Keep on talking about dust. Is there different chemical compositions of dust in different galaxies?
So that's a really good question. That is something that we will be able to answer better with James Webb. From my research, from what I can tell, there's not. The galaxies that I work with all have the same metallicity. And I don't see, the other thing that we might expect that would change our calculation of dust mass would be an increase of ices. And I've looked for that as well. I don't see it. But the data that I was working with are not the highest quality because it was the Spitzer Space Telescope. So it's really an unresolved question as to how. So if you change the dust population in galaxies, you could change the dust mass quite significantly and get rid of some of that scatter.
It looks like the theoretical relation goes through the low-Z points reasonably well.
Yeah.
I guess. Oh, it's only the high luminosity points that goes.
Yeah.
Sorry.
That's okay. Okay. So that was a plot from my rejected ALMA proposal, but that's okay, because I now actually have the observations to be able to do this, to measure, make similar plots like this for local galaxies from high Z galaxies using ALMA data. Okay.
Excuse me,
yeah.
The orientation of a galaxy playing a role here?
Yes, that is another unconstrained parameter. For this particular, no, because all the galaxies are unresolved and they're point sources. When you do a resolved study, yes, you need to account for the amount of material, yeah, in the inclination. So for local galaxies, for example, I tried to choose face-on galaxies to ignore that. All right, so now we get to the really interesting question, is why are these galaxies so dusty? What is going on 10 billion years ago that these galaxies would have so much more dust? So initially we thought, well, maybe they're just more massive. So we plot stellar mass versus dust mass, and all of my galaxies are the same. Okay, they all span the same range. just as a side note, just to let you know that the dust is an ongoing theoretical study as well. These are the theoretical models for how dust mass should evolve with stellar mass, and of course the observations don't match them at all. And that's because dust populations, it's still an ongoing work to understand dust populations in galaxies. So one of the things that we do know is that the gas fraction of galaxies evolves. So this is the fraction of the mass locked up in gas in a galaxy. And this evolves with redshift because we think that there was just more gas around in earlier times to fall onto the galaxy. So this is the measured relationship of gas fraction versus redshift, and it increases with time. So what I did is for a galaxy at this particular mass, I just said, what if we just evolve its gas fraction? What would happen? And we assume a constant dust to gas ratio. Well, what you get is that dust mass. So it matches the observations really well. So what we think is happening is just that these galaxies at earlier redshifts, they have more gas. So they have more dust because they have more gas. They are less efficient at forming stars because they're more spread out in a disk, whereas their local counterparts are all forming stars in the center, and that makes them highly efficient at forming stars. So it's kind of a complicated picture of what's going on, but we're seeing big gas-rich disk galaxies.
And I'm sorry if I missed this. The super sample, your high Z sample, these are main sequence galaxies.
Yes.
So, sorry.
Exactly, yeah. Okay, so there's more gas around. This gas is fueling stars, and it's also fueling black hole growth. So now I'm going to transition and talk a little bit about what we think is going on with the black hole at the center of these galaxies. So first of all, we think that black holes are really important in galaxy evolution because we know that the mass of the central supermassive black hole is tightly correlated with the mass of the stars in a galaxy. It follows a correlation that we can witness out to redshift of 2. So what has been inferred from this is that there must be a feedback process from the black hole that is regulating the growth. That hasn't been seen yet. That may or may not be the case. But we do know that something pushes galaxies from the main sequence down to the quiescent regime. Something has to quench star formation in a galaxy. Black hole feedback is one mechanism that is capable of doing it, although it has not been seen universally. So one of the things that I am interested in is how many black holes are there. There's a missing population of black holes. We don't know about them because all we know about in galaxies are like the very luminous, the easy to find black holes. So I'm interested in finding less luminous black holes. And then I want to know where they lie and with respect to the main sequence. What is their role in galaxy evolution? So the best way to find black holes is with spectroscopy. Specifically, I think mid-infrared spectroscopy. This is work that I did with the Spitzer Space Telescope. These are real spectra of real galaxies in the mid-infrared wavelength range. James Webb, which is launching next year, is going to cover the same wavelength range with a much, much better spectrometer. So what I do is I take the infrared spectroscopy and I fit it with a multi-component model of star formation features. So that's these. These are called polycyclic aromatic hydrocarbons. They're fragile little grains. They live around newly formed stars. Every time we see them, we know that there must be star formation. We have them here on Earth as well. Have you guys ever heard of PAHs? Okay, yeah, they're carcinogenic. You have them in cigarette smoke. So you can always use that. I don't know, I like to impress my friends with that fun fact about PAHs. And so with an AGN, though you don't see the PAH emission, you just see a pure power law emission. So an AGN is an active galactic nucleus. It is a black hole that is actively accreting material from an accretion disk, and you have a dust torus surrounding it. And this dust torus heats up to many, many different temperatures, and the radiation of this torus radiates like a power law. So that is what you're seeing here. And then, of course, you can have some extra extinction component, in this case, silicate extinction. And then composites are kind of the perfect mirror, perfect mix of star-forming galaxies and AGN. They've got this torus component, and they have those PAH features on top of it. And so the nice thing about spectra is that I can decompose it to quantify the amount of luminosity due to an AGN heating. So that's this fraction down here. It is the fraction of mid-infrared light coming from a growing black hole. Now, to return to the idea of the whole infrared spectrum, the mid-infrared does relate to the entire infrared spectral energy distribution. So the mid-infrared was just this part right here. So for a star-forming galaxy, you have a stellar bump. So this is light from basically the old stellar population. Then you have these PAH features, and then you have a lot of cold dust. The cold dust is due to the interstellar medium, the diffuse interstellar medium, like in the disk of the galaxy. When you have a growing black hole, again, you just see this pure power law spectrum. You see this cold dust, and then you see this warm dust as well. I'm going to talk about this warm dust in a slide, another slide, because I think that this component is also coming from the black hole. Composite is, again, the perfect mix of the two. You can kind of just see how you would add these two together and get a composite galaxy. So these are empirical models that I created from galaxies, from real galaxies. The value of having these kind of empirical models is that normally what you see is these 5 data points. That's what we did in this paper. We had these data points, and we took templates, and we fit them to determine that that galaxy is a pure star-forming galaxy, and it's not hosting a luminous AGN, which we might have thought just based on its luminosity. Okay, so high redshift photometry, it's not very much. It's kind of hard to glean information. All right, so from these empirical templates, I measured the temperatures in the galaxy, like of the dust in the galaxy, and I found 2 interesting correlations. First, that the amount of cold dust in a galaxy is relatively steady, but it falls off as your AGN grows. And then I found that the temperature of this warm dust component increases steadily and then flattens out with an AGN. What I think that this is telling us is that the heating from the black hole is actually propagating into the galaxy itself. And it's not just in the torus. And the reason is that I'm measuring 80 Kelvin dust. I don't think that you expect to see 80 Kelvin dust right next to the black hole. I think you expect to see 80 Kelvin dust further into the galaxy itself. So this is like kind of the first tentative evidence that AGN might be having a much larger effect on their galaxy than previously thought before. Okay, I just wanted to advertise one of my student work who showed that having hidden black holes really matters when you're calculating star formation rates. On why you really need to be careful. If you read the literature and you read star formation rates, what they will usually do, you usually only have a couple data points. People will take one template, they will scale it to a data point, and then integrate underneath it to calculate the star formation rate. What people usually do is take a star formation template and just scale it to this data point right here. In this case, the star formation was very wrong because there was a hidden black hole nobody bothered to look for. So when we looked for it and we found that you need to use instead an AGN template, or you can overestimate your star formation rate by a factor of 5. Going the other way, the other thing that people do at high redshift is they take a template and they scale it to a far infrared data point, and they again calculate a star formation rate. In this case, there were other signatures of a black hole, so we figured that the infrared luminosity might be coming from a black hole, but it wasn't. It actually looks like a pretty classic star formation rate spectrum. So you need to be careful both ways, because if you apply an AGN template to a star-forming galaxy, you can overestimate the star formation rate by a factor of 3. So all this means is that if you are the kind of person who does studies at high redshift using star formation rates determined from the infrared, they could be wrong. And in fact, people in the literature, most of the literature is not careful about this. Okay. It's an application to even higher redshift of what you can do once you understand the AGN and the star formation component. This galaxy is at redshift of 4.12, so that's like a gigayear after the Big Bang. This is the highest redshift detection of a PAH feature. All right, so this is the farthest away that we have seen this tiny molecule. This again tells us something about the dust grains in a galaxy and the dust population in these galaxies. I was able to determine that the star formation rate in this galaxy is 700 solar masses per year, so it has a gas depletion timescale of 24 million years. So that's really short. So this galaxy, it's on its way to quenching, we think. Now, the black hole can also...
Can I ask a question about that?
Yeah.
The depletion timescale assumes a constant star formation rate, right? So when you go from the star formation rate and the mass of gas, which you're getting from actually, I don't know what you.
CO.
So you get, okay, so assuming your CO is right,
Yeah.
and the star formation rate is what it is,
Mhm.
depletion time makes some assumptions about what the star formation history is, and also that it's closed box, right?
No, the depletion timescale is just
There's
this.
no new supplies of gas, basically.
Right.
That's
Yes.
what I mean,
Exactly.
closed
Yes.
box. There's
Yeah.
no
Yeah. Yeah.
inflow,
Yes.
so
Right.
do you know that it's quenching, or do you just know that it would
No.
use up the gas that has?
No. If this was the only gas supply it had,
Okay.
that would be on. Yes. Right. So we also have the first indications that AGN can seriously affect carbon monoxide in a galaxy. So carbon monoxide is, we use it as a tracer for the fuel for star formation because we can't actually see very cold molecular gas. So instead we look at carbon monoxide. Up until this, the common assumption is that CO doesn't affect, or that the AGN and a growing black hole does not affect lower transitions of carbon monoxide. It only affects the higher transitions. But what we did, is we went back and we scanned the literature and we compiled samples from the literature that had an infrared spectroscopy so I could measure their AGN component, and it had multiple CO transitions measured. So this is all redshifts 1 to 4. We stacked them all and we found that the AGN component seems to have a different CO energy distribution than star-forming galaxies. This is really important when you're trying to basically convert CO to a gas mass. And this is something we have very large error bars on, small sample size. We're currently applying for more time to be able to beat down this noise. But now that we understand this pretty well, we can ask, does a growing black hole at all correlate with the gas depletion timescale? And so for this study, I calculated the black hole accretion rate from infrared data and the gas depletion timescale, assuming a closed box. And from redshift 0 out to 4, we find that there is no obvious correlation between a growing black hole and a gas depletion timescale. But if you had not carefully decomposed star formation rate, you would see a very strong correlation. Now, this plot doesn't tell us a whole lot because it's data mined from the literature. If I had seen a correlation, I would have been suspicious of it. But what it tells us is that we need larger samples of growing black holes. And so for that, I turned to the CANDLES fields. All right, so CANDLES it was an optical survey, but they all have infrared data. So I took their infrared data to find how many of these galaxies in this image have a black hole. And the best way to do it, I'll just walk you through it really quickly, is with colors. You can do it with infrared colors. So this is my library of models going up with the growing black hole. If you measure the stellar bump, and then you can compare it with the amount of cold dust to warm dust, you find that star-forming galaxies live in this regime, and growing black holes live in that regime, and then the composite galaxies live in the middle. Okay. So I was able to measure the first census of hidden black holes at redshifts of 1 to 2. And we do this with number counts. So this is the number of galaxies that is greater than a certain 24 micron flux limit. So it's just an infrared flux cut. The pink line, just to impress it, that's all the galaxies in the universe shining in dust. Okay. The black line is all of the galaxies at redshift of 1 to 2. So the cosmic noon era. So I took the black hole line and I split it up into my 3 different populations of star-forming galaxies and AGN and composites. And what I found is that composites account for 30% of any population. The orange line, we knew about this pretty well. We knew it with X-ray telescopes because 75% of really luminous, dusty, luminous AGN you can also find with X-rays. It's the purple line that's new, that this is kind of discovery space. So this means that with future infrared telescopes, we are going to be able to find, like anywhere you point your telescope, at least 30% of the galaxies you're looking at have a black hole. So if you want to understand black hole growth and galaxy evolution, infrared is the way to do it. And so now that I have this big population of galaxies, I can put them back on the main sequence, on this AGN growth, okay? I find that the dusty galaxies are all on the main sequence for the most part. Non-dusty galaxies of the same stellar mass and same redshift range all lie below it. But this isn't actually the best way to look at this. The best way is through a distribution. So here's our main sequence. Star-forming galaxies lie on the main sequence or slightly above it. Non-dusty galaxies lie in the quenched regime. Composites lie slightly, it's about a 0.3 dex shift below star-forming galaxies, and AGN lie even more below that. So this is the first hint of a systematic shift. As your black hole grows, you can imagine an evolutionary sequence from star-forming galaxies to composites to AGN to dusty galaxies, or to non-dusty galaxies to quenched galaxies. But there's a couple problems. The reason that you want to look at huge statistics, so this is thousands of galaxies to be able to get these nice distributions. The reason you want to look at big statistics is that black hole growth isn't constant. Black hole growth flickers. It flickers on and off. So you can imagine that something is a star-forming galaxy for a while, then its black hole starts to grow a little bit, but then it quenches and it goes back to being a star-forming galaxy, but then it grows some more, and it kind of bounces all over this regime. As long as the time scale for that is short, then you should still be able to see this flow. And we can calculate, one of the things I'm working on next is using these kinds of population statistics to calculate the time scale of black hole growth and when black holes start to shut down star formation in a galaxy, if they do. They might not at all. This might also just tell us that black holes only grow at a very specific time in a galaxy's life. Okay, they might not affect the star formation at all. Now, there is a problem with this plot, though, and that is that up until this point, I have been talking about observable signatures of black holes. I'm just measuring the amount of mid-infrared light that I think comes to a black hole. I'm not actually measuring anything physical about the black hole itself. So what I did, I had a summer student who calculated the black hole accretion rate of all of my galaxies, and it's kind of hard to see. But this is, again, star formation rate versus stellar mass, and now points are color-coded by black hole accretion rate. Black hole accretion rate is actually increasing with star formation. All right? They're not anti-correlated, they are directly correlated. So that's kind of problematic. And not only that, you can take this one step further and talk about a black hole efficiency rather than just black hole accretion rate. Black hole efficiency is basically how much your black hole is accreting versus how much it could be accreting by its theoretical limit. All right, and so I calculated that as well. So this is black hole efficiency, so how much it's accreting versus its theoretical limit, versus my observational signature. And they're not correlated. There's a broad distribution of both. And so if we return to that idea, that main sequence distribution.
Sorry.
Oh, sorry.
You said they're not correlated, but.
Oh, they are, but there's a broad distribution.
It's really a systematic shift.
Yeah, there is a systematic shift, but it's not a one-to-one correlation. That's what I mean, sorry. Okay. So I could classify something as an AGN, but it could be a very low Eddington AGN. I could classify something as a star-forming galaxy, and it could actually. So not disjoint sets, there's heavy. Yes, right, yeah. Right, and so this brings us to an interesting problem, which is that if you put them back on the main sequence, you see not that clear pattern anymore. So now low Eddington objects lie slightly below the main sequence, as do high Eddington objects, and it's these mid-range efficiency black holes that lie on the main sequence. So the problems are selection bias. So far we don't have an unbiased selection of AGN, even in the infrared. The other problem is how well do observables trace physical parameters. I'm taking an infrared luminosity, I'm directly converting it to a black hole accretion rate. I've made a lot of hand-wavy assumptions there, so that could be wrong. And just incompleteness due to existing techniques. But the future is here, and the future is James Webb. And James Webb is going to solve a lot of these problems because, so this is a Hubble image of galaxies. This is what Spitzer saw. This is what I was working with my previous infrared data. Same field of galaxies. James Webb will see this. All right, so it's going to break up these big blobs of light into all the distinct components, little galaxies. There's no more guesswork anymore, and it's going to have just like a ton of filters, way more filters than Spitzer had. So James Webb color selection, that same idea of just putting a filter on different places on your infrared spectral energy distribution, will be able to better separate star-forming galaxies from growing black holes. So this is something I determined optimal. I optimized James Webb color space, by simulating galaxies. So this is all just a Monte Carlo simulation of what the real scatter of galaxies that I think we'll have. And so you can see the colors indicate a growing AGN, and you can actually separate things very nicely by color. So we'll be able to measure that AGN fraction with just a few bands of color as well. And that's because the way we are sensitively tracing those PAH features versus this dip due to the old stars. So what I predict we're going to see, so I've made a prediction for number counts of low Eddington objects in the era of James Webb. I've done this by using the Candles galaxies and scaling their 24 micron counts. This black line is the entire population that I think that we will see at redshifts of 1 to 2, and this is how I think it's going to break up. Again, the yellow are really actively accreting black holes. We can see those with the X-ray. The pink line is stuff that we're not going to be able to find. We're not going to be able to measure black hole growth even with James Webb. They're just going to be too faint. But the purple line is everything that we will be able to measure a growing black hole in. And so that's going to help us fill out that main sequence diagram. Not only that, I have calculated this as the number per one field of view. So one pointing of the telescope. You're going to open the shutter once. You're not going to have to move your telescope. And we're going to find 100 objects. And we're going to do it in less than 5 minutes. So we're going to just really build up our population statistics with this telescope. And then this area right here is low mass galaxies. So it's everything less than 10 to the 9. This is where the dust population is changing. So I'm not entirely sure actually what their pH features are going to look like or what their black holes are going to look like. So it's essentially discovery space. Those are the predictions I've made, but that could be completely wrong for low mass galaxies. It's going to be hopefully one of the first things that I look at. The other thing I just want to just briefly show you how much better the spectroscopy is going to be as well. So this is what I was dealing with before. This is Spitzer spectroscopy. This is going to be Miri spectroscopy. So the AGN lines are shown in red and they just pop right out even when you have star formation laid on top of them, which is good because we will be able to calculate black hole accretion rates from these lines themselves. And in fact, this plot up here shows basically the black hole accretion rates we will be able to detect in 6 minutes. The thing to note is that the black line is what we were able to do with 200 hours of Herschel data. And each of these lines are the black hole accretion rates we'll detect in 6 minutes of James Webb time. So it's going to be really impressive. It's going to open up a new regime of black hole studies. Okay, so just to conclude, found that dusty star-forming galaxies have 5 times more dust mass than their local counterparts, but this is due to the existence of a lot of gas at high redshift. All dusty galaxies are right around the main sequence, regardless of whether or not they host AGN, but active galactic nuclei have less star formation than normal infrared galaxies. So this indicates that the black hole could be responsible for quenching, or it only occurs during a special stage of galaxy evolution. However, I know that we're still incomplete, working on ways to correct for incompleteness, but James Webb is going to really help us push down into that low efficiency black hole regime and hopefully catch black holes before they have a big effect on their star-forming galaxies so we can understand them in the broad picture of galaxy evolution. All right, thank you.
The dust has to be made by the stars.
Mm-hmm. Yeah.
So your very earliest, when galaxies first start, there's no dust?
That's right.
And we see those galaxies, do we?
Some people think that they do. Yeah. Yes. We think that we have found redshift 10 and 11 galaxies. Yeah. James Webb will do that better. The mission of James Webb is to find the first galaxy in the universe. So we don't know what redshift, that we think maybe redshift 12, but possibly 14.
Okay. And then when you talked about that, you have this sort of the spectrum coming out. I mean, is this like global warming? Is all the heat eventually emitted, or does some of this, the fact that you have this dust, increase your black hole accretion rate or your star formation rate just because you're trapping stuff inside, so to speak?
So no, it's a good question. The answer is no, because the dust emission, primarily most of the dust emission comes from the diffuse ISM, so not star-forming regions. So the radiation does leak out of star-forming regions, and then it heats the big dust grains within the interstellar medium.
Okay, so most of it is.
Yes.
John?
Question about supernovas. So, type 2 supernova, type 1A supernovas are so important for dark energy, and the supernova people have models of dust, and those models have been around, I think, before this kind of work. So do you have the same world view or universe view of dust? Do you agree with the supernova people on dust? Do you disagree?
Yeah, okay, so that's a good question. So the supernova view of dust is mainly, well, I guess it's both how it's created and how it's destroyed. The dust that I'm working with, we think is created within the interstellar medium itself. We don't think it's initially created from supernova, but it's controversial. Actually, dust models it's not settled. It's ongoing area of research. It's not quite what I do. But we think that basically the destruction rate of dust in the interstellar medium is long enough that if dust was only produced by supernovas, you would never see a dusty galaxy. So that dust grains must reform and grow more within the interstellar medium itself.
Barb?
Can you draw a line, a little bit more connection between the emission line, I assume equivalent width for particular features, and the black hole accretion rate?
Yeah, we think it comes from basically the broadline region around the black hole. So as big as the equivalent width is, you can fit a Gaussian and figure out how fast things are moving, and then how fast things are moving would be the black hole mass.
I was trying to work the equivalent with, couldn't make that concept work. Thank you.
Michael?
You were talking with the James Webb, you wanted to make these ratios of different colors. But isn't that just using a small fraction of the information, and won't you somehow try to fit, like, I don't know, you have 11, how many colors will you have? You'll have 11 colors or something? Or?
Yeah, so it gets pretty dicey. The longer wavelength filters have much poorer sensitivity, so we likely won't observe with them. So with the shorter filters, yes. So this kind of work is useful for people who primarily want to look at the near infrared, and I'm trying to convince them to look at the mid infrared as well, and then you only need 4 filters, and it's an easy sell. Ideally what you want is all of the filters from the near infrared to the mid infrared, and you want to combine it with the optical, because then you can really split your galaxy up into an accretion disk, a stellar component, a torus, and all those things. But we don't have that for every galaxy.
You won't observe that.
Right, it won't observe that for every galaxy. So the galaxies that we do have it, we can do that. Colors are really useful when you're data mining and there's just not that much information there, or they're really useful to select a certain population to go observe in more depth.
So I have a question too about this link between the black hole fraction, AGN fraction, and quenching. So one of these was you showed that the temperature of the dust was increasing as you went to a higher AGN fraction, and you said, oh, it gets up to 80 Kelvin, and therefore this must be dust heating throughout the whole galaxy, because I can't imagine the dust being, couldn't that could just be from the torus or something? I mean, I guess I'm wondering, like, couldn't it just be a hot torus? Like, how do you know, do you have radiative transfer models that like kind of done full radiative transfer of AGN light through a galaxy to show that the only way to get the global dust temperature up to 80 Kelvin is from, sorry, maybe I mixed this, is from black hole light leaking in, or could it just be the hot torus right around the black hole and not actually be influencing the global host properties?
Right, okay.
So that was a really long question because I was trying to work out the chain in my mind from the dust temperature to a causal.
Okay, so radiative transfer is one of the projects that I want to do because I had to have a good model of AGN emission. So we think that we have that now, so now we can just start dumping dust on it. But the torus dust is usually at 1,000 Kelvin.
Okay.
So 80 Kelvin dust is typical. It's a little bit, it's close to what you would see in a star forming region. So we don't think that that exists that close. But no, we have not done radiative transfer.
If the AGN, do you know if the AGN, and I forget if you showed this, if the AGN fraction is higher for galaxies that are smaller? At a given mass, that is, will galaxies be more compact? I know there's people in literature who are saying that when you get AGN, you get more compact galaxies, and that will increase the radiation field and also the dust.
So they don't have a complete selection of AGN, so I don't think you can say that.
Okay. The second question I had was, you said that as you go to higher AGN fraction, you're shifting systematically below the main sequence.
Yes.
That was one of your later plots. How confident are you that this is not, because for your highest AGN fraction, you're now measuring the star formation rates for a relatively small amount of emission.
Yeah.
So how confident are you that this isn't just a systematic error in how well you're decomposing AGN and star formation?
That I'm very confident on, because also measured the star formation through full UV optical fitting as well. And when you sub in those star formation rates, you see the same shift.
Okay. Any other questions? Okay, great. Well, let's thank Dr. Kirkpatrick again.